Hey, welcome back. In this lecture, we're going to talk about the addition of hydrogen halides to alkenes, which are very commonplace on the DAT. So, when looking at alkenes and hydrogen halides, we need to notice that the alkene has a double bond, of course, and there's a lot of electron density in that double bond. And then a hydrogen halide, of course, has a very large dipole with a positive charge mainly on the hydrogen and a negative charge on X, which is going to be any kind of halide, chlorine, fluorine, iodide. So, what happens is the double bond comes out and the electrons will pick up the hydrogen from the hydrogen halide, and the electrons in the hydrogen halide bond will go over to the halogen. Once this happens, we're going to, very important concept is we're going to get a carbocation formed on one of the carbons of the alkene, and then we're going to get the halide with a negative charge on it. Once this happens, this is the rate limiting step. The negative charge from, or an electron pair from the halogen will come over and it'll attack the empty p orbital of the carbocation, and then we'll get our product over here, just adding a hydrogen and a halogen across this double bond. So here's a quick example, a real example of 2-butene. We're going to have 2-butene and hydrogen bromide, and then through the mechanism that I showed you, hydrogen is going to add to one carbon, and then the bromine is going to add to the other carbon. Pretty simple mechanism, pretty simple concept, but it gets a little bit more difficult from there. What if the alkene is not symmetric, like in 2-butene? What if we have a terminal alkene like pentene right here? Where's the bromine going to add, and where's the hydrogen going to add? Is the hydrogen going to add here or here? Is the bromine going to add here or here? Because you're not going to get the same product if it adds at different places. And we have to go over the concept called Markovnikov addition. So the basic mechanism, like I showed you, is the double bond comes out and it'll grab a hydrogen, and then the electrons in the bond will go to bromine. If this happens to where the hydrogen becomes attached to the second carbon of the alkene, then we're going to get a primary carbocation formed. But if the hydrogen attaches to the primary position on the alkene, then we're going to get a secondary carbocation that is formed. So Markovnikov's rule says that hydrogen is going to add in such a way that you're going to form the most stable carbocation. We all know that primary carbocations are extremely unstable, and secondary is far more stable, followed by tertiary being the most stable of all the carbocations. So when adding HBr across this particular alkene, we're going to form the secondary carbocation, the more stable one, and so this intermediate up here is not going to be formed whatsoever. So once we form this intermediate down here, bromine is going to add to the carbocation, and we're going to get Markovnikov addition of the addition of hydrogen bromide across this alkene, which means hydrogen adds to the least substituted carbon, and then the halogen is going to add to the most substituted carbon on the alkene. Again, we need to understand carbocation stability. Tertiary is more stable than secondary, which is more stable than primary. Alright, so now we need to go over something called the carbocation rearrangement. And again, it's all about forming the most stable carbocation that you can. Alright, so again, the double bond comes out, and we'll grab a hydrogen, and those electrons will go to chlorine in this case, and we're going to form a secondary carbocation in this case. Very stable carbocation, and if chlorine were to come and attack this carbocation, we will get a product that looks like this. But unfortunately, this is going to be our minor product. And why is this our minor product? It's because we have a hydrogen sitting right here on this tertiary carbon. And what can happen is what's called a hydride shift. The electrons in this hydrogen-carbon bond can move over to this carbocation. And if that happens, then we get a carbocation at this tertiary carbon, forming a tertiary carbocation, which we know is more stable than a secondary carbocation. Carbocation rearrangements can only happen with adjacent carbons, right? So if this tertiary carbon was more than one carbon away, it's not going to move over to form the tertiary carbocation. It's only going to happen on adjacent carbons. So now, if chlorine comes in and attacks this carbocation, we're going to get this product, which is going to be our major product. All right, so that's how carbocation rearrangements formed. You definitely need to look out for these on the DAT. If you see one, if you see a position adjacent to a carbocation that you can form a more stable carbocation, you need to do it, and you're going to form the more major product that way. All right, so let's do an example quickly to learn what we just went over. Why don't you pause the video, take a minute, try to solve this problem. Problem asks, what's the most stable intermediate of the following reaction? Alright, for this reaction, we know that it's just going to be an addition reaction of a hydrogen halide. So the double bond comes out, grabs hydrogen, and then we're going to form our carbocation intermediate, which is going to be secondary. Very stable, but we have to look, can we form a more stable carbocation from adjacent carbons? And we notice that the adjacent carbon here is tertiary with a hydrogen on it that can move over to this carbon. Once we do this, we can actually form a more stable tertiary carbocation here. So this is going to be our most stable intermediate in this reaction. Alright, so if we look at this reaction, addition of a hydrogen bromide across this double bond, we're going to get Markovnikov addition. We're going to get the addition of the bromide to the more substituted carbon of the alkene. But what if we don't want to do that? What if we want to add the bromine to the least substituted carbon? Is that even possible? And it is, and we have to use peroxides to do that. So you're going to see this probably on the DAT. You're going to see something funky where the bromine is adding to the least substituted carbon. You're like, hey, how's this happening? But it's happening through peroxides. And if we use a peroxide, then we're going to get what's called the anti-Markovnikov addition product. So this reaction happens through a radical reaction. First, we're going to take the peroxide and we're going to homolytically cleave this bond, which means one electron goes to one of the atoms and the other electron in the bond goes to the other atom. And we're going to get a radical, a hydroxyl radical out of this reaction. This radical then reacts with hydrogen bromide. In this fashion, another homolytic cleavage happens, and we're going to get water as a byproduct, and we're also going to get a bromine radical as our other product. This bromine radical is then going to react with our alkene. So this step right here is going to allow us to know where the bromine is going to add. Just like carbocations, radicals want to be on the most substituted carbon as well. So since we're adding bromine first in the anti-Markovnikov addition instead of hydrogen in the Markovnikov addition, we're going to add bromine to the least substituted carbon because we're adding it first and we're forming a stable secondary radical. If bromine were to add to the internal position, we would get a primary radical instead, which is far less stable, just like carbocations. So now how do we finish out this reaction? This radical is going to react with another molecule of hydrogen bromide. We're going to get out a bromine radical, which is just going to continue on and do the same thing with another alkene. And then we're going to get our product, which is the anti-Markovnikov addition product. Bromine's adding to the least substituted carbon, hydrogen's adding to the more substituted carbon. And this is all because we're using peroxides in the reaction. Alright, so here's another example. We're going to do an anti-Markovnikov addition example because we're of course using peroxides. So take a second, pick the most likely product out of this reaction, and then we'll go over it together. Alright, so like I said, this is going to be an anti-Markovnikov addition product. We recognize this because we see peroxides in conjunction with the hydrogen halide and an alkene. So in this reaction, the fact that we're just recognizing that we're using peroxides, we don't really need to draw any kind of a mechanism. We just know that the bromine is going to add to the least substituted carbon now, and your hydrogen is going to be adding to the more substituted carbon. So B is going to be our answer. Alright, so quick summary of what we learned in this lecture. We learned that Markovnikov addition of hydrogen halides across a double bond happens in a fashion that we form the most stable carbocation, which is on the more substituted carbon. And then once you form that carbocation, you have to be aware of something called a carbocation rearrangement. So if a hydrogen can move from an adjacent carbon to form a more stable carbocation, then it's going to happen, and that's going to be your major product instead. And then we learned about anti-Markovnikov addition of hydrogen bromide across a double bond. This happens with peroxides, so just recognize that if you see peroxides in this reaction, then you're going to add the bromine to the least substituted carbon. The hydrogen is added to the most substituted carbon. And this goes through a slightly complicated radical mechanism. And when looking at the radical mechanism, just know that the radical likes to be, of course, on the more substituted carbon, just like a carbocation would like to be.